Hello, I'm Ashton Rowe, and I'm studying electrical and computer engineering.
I'm Harrison Pearl, and I'm studying software engineering.
I'm Marcel Merrill, and I'm studying systems engineering.
I'm Ellie Griesmer, and I'm in mechanical engineering. I'm also our team lead.
I'm Mari Nath. I study electrical and computer engineering, and I'm our procurement lead.
My name is Luis Ruiz, and I'm studying mechanical engineering.
Our project is the Wireless Emergency Lighting System Battery Tester, sponsored by Parker Miggett.
So, what is the Wireless Emergency Lighting System? Its green signs are pictured here, which get installed inside the Boeing 787 Dreamliner to guide passengers to safety in the event of an emergency. In order for this system to be reliable in that event, it must be powered by a reliable battery. That battery is pictured here, known as the Wireless Emergency Lighting System, or WELS, battery unit. To ensure this reliability, each battery must undergo strict quality control. The battery parameters to be verified include charging to 8.2 volts DC when full, discharging at expected levels according to the battery cell ratings, responding to unsafe currents through the protection circuitry, accurately reading the temperature, having an accessible memory with serial number and manufacture date, and lastly, conforming to the set levels for storage and shipping. Here's where our project comes in. Seen here is the sequence of tests our device will perform on a connected battery. You'll notice some functions like the charging and memory modification can be performed individually rather than in the full quality control cycle. This device is not new. It's currently verified by the device pictured here. The device can no longer be made due to its parts obsolescence, and therefore it has limited the number of new batteries that can be manufactured and verified in a timely manner. The device is unnecessarily complex, using more than 50 custom pieces and connecting to 6 batteries at once. Its connection to the batteries is poorly secured by the acrylic casings seen here on the top of the device, and lastly, its software and design were poorly documented. Our device, the WELS battery tester, will make 2 main improvements. These are improved manufacturability and modularity. The modularity allows us to simplify the design so that we charge and test only one battery at a time. This not only gives our sponsors flexibility on the quality control production floor, but it also allows the device to be sold to Boeing just for their use as a charger. With this design change, you might be wondering how we plan to meet the same testing times as the previous device, which tested 6 batteries at once. The modularity of our system allows up to 6 testers, each with their own battery, to connect with each other. This way, the power input is shared, the data is exported through just one connection to a host computer, and the interactions to initiate a test sequence can be shared. For the manufacturability aspect, our team has maximized use of off-the-shelf parts and minimized our bill of materials. We've also ensured that the electrical connection can be maintained with an improved design to secure the battery to the tester. In just a moment, we'll dive into the specifics of our device's design and how it interfaces with the battery. To preface this, we will first briefly review the requirements we created to help conceptualize our device's core functions. We have 3 sections of requirements. First, and most importantly, are the performance requirements. These include verifying the battery's key parameters like store charge and voltage. In this section, we have also required that the time it takes to evaluate each parameter meets the time taken by our legacy device. We have also required that our charging circuitry varies the current it uses to take measurements from the battery so that it's always operating at safe levels. The second section of requirements determines how our device interfaces with its system boundaries, our most important system boundary being the battery itself. Here, we have also required our device to follow standards for portability and ease of transport. For the software program, we have specified what options a user has when selecting a test and how long it takes for the system to initiate a user's requested test. In the third and final section, we require that the device monitors its own temperature and the battery's temperature. Dependent on these measurements, it can issue commands to shut off the entire modular system if a temperature falls outside of safe ranges. With our electrical system being the most integral and complex to our project, we're going to first review its components in detail. The microcontroller we've selected is an Arduino Nano. This allows us to connect decisions made by a user in the software to testing values applied by the circuit to the battery. Next up is the charging circuitry. The charging IC and associated components are contained within an evaluation board purchased by Texas Instruments. This charging circuitry allows us to manage charge states and ensure battery safety. Next up is the discharging circuitry. With the different loads that it contains, we are able to simulate use case scenarios and verify that the battery responds appropriately. We did plan to manufacture a custom PCB to implement our electrical design. However, due to several issues that we will discuss in more detail on Design Day, our design is now made possible by breadboarding and prototype boarding. Finally, our electrical design has accounted for modularity in several ways, notably in the power input. When several testers are connected in a modular system, the testers will be in parallel with each other so that each device receives 12 volts DC.
Here you can see the electrical components of our testing device connected to the battery. In this configuration, you'll notice that only the set of electrical components that Ashton is currently pointing to is connected to a battery. The second Arduino and breadboard pair is only connected to the first device in order to demonstrate the modularity, and is not actively connected to a battery. Shortly, Ashton will point out the flashing light on the second pair that proves it has successfully received a command from the software program.
First are prompted with a place to save our output. As you can see, we've selected the demo directory. Now you can see that we have 6 WBTs connected, all with the connected status. We can control them from the master, which will send a command to each device, or we can control them on an individual level. Starting on the individual level, we will do the full ATP. And then we click send command, and then we get data. It should be noted that the data in this demo is not actual data, rather a test script created for the purposes of this demo. Additionally, we can stop this test by telling the device to shut down, and then it will shut down. Further, we can go into the master drop-down window, select charge, and then send command, and then all the devices will begin transmitting data. You can stop individual WBTs with the shutdown, or you can stop all connected devices with the shutdown. This has been the demo of the WBT control software.
The mechanical efforts have focused on adapting to the needs of the electrical team and testing small sections of the housing, as represented here by the black and red prints at different stages of design. The scalability and manufacturability of the design have guided us consistently. Here you can see what 3 WBTs stacked together modularly would look like as a system.
We'd like to take the time to thank our sponsors at Parker Megget as well as our mentor, Jim Sweetman.
We'd also like to thank the IEEE University of Arizona Student Branch, particularly Jeremy Sharp and Calvin Holmes, and Bob Garcia.
Thank you, and we look forward to seeing you at Design Day.